On the previous example here, on example 10, I neglected to show you the graph that puts all of these little pieces together. So here is the graph of 1/2 x minus sine x over the open interval from 0 to 2 pi, along with its derivative, 1/2 x, no, it's just 1/2 minus cosine x. I believe that's what it was. And then along with its critical numbers and linking those critical numbers to the relative mins and maxes. So I have a relative minimum right here at, I believe it was pi over 3, because the first derivative changes from negative to positive right there at 5 pi over 3. And then over here at 5 pi over 3, we have ourselves a relative max because the derivative changes from positive to negative. Okay, let's look at example 11 then. Find the relative extrema of f of x is equal to the quantity x squared minus 4 to the 2/3 power. So when it says relative extrema, I know that I'm going to use the first derivative test to find relative min and maxes. And that whole entire process begins with the first derivative. So let's find that. First derivative, f of x is equal to, leapfrog the power down, 2/3 x squared minus 4, subtract 1, negative 1/3, and then this is a composite function, so don't forget to multiply it times the derivative of the interior, which is a 2x. All right, let's clean this up. F prime of x is equal to, this 2 is going to stay on top with the 2x to make 4x. The 3 is going to go on the bottom along with this cube root to make 3 times the cube root of x squared minus 4. All right, critical numbers, easy. Where's the top equal to 0? Where's the bottom equal to 0? Top is equal to 0 at x is equal to 0. The bottom is equal to 0 at, let's see, x squared minus 4 is equal to 0, so that's plus or minus 2. X is equal to plus or minus 2. Okay, so the reason why plus or minus 2 are critical numbers, it's because where the derivative does not exist. But if I look at the original function, its domain is all real numbers from negative infinity to positive infinity. Okay, but the derivative does not exist at positive or negative 2. I wonder what's happening on the graph at those particular points. You know what can help us put those pieces together? The first derivative test. Now, you don't necessarily have to label this the first derivative test. I'm just, I'm making a video here for you to learn by, so I'm labeling stuff, being as thorough as possible. Okay, so we need to make ourselves some intervals. And it was all real numbers that we have to break up with our critical numbers. And the first interval is going to be from negative infinity to negative 2. And then we have one from negative 2 to 0, I believe. From 0 to 2. And then Buzz Lightyear's favorite, from 2 to infinity. Okay. Wow, look at that table. It looks so, I don't even know, lopsided. Okay, so now we need to take some test values in each one of these intervals. Pick something easy, like negative 3 million, negative 1, positive 1, and then a positive 3 million. And where do these test values go? They go into the first derivative in order to see, is the first derivative positive or negative? And just for convenient, I'm going to rewrite that first derivative right down here. And it was 3 cube root x squared minus 4. Okay, so plugging in a negative 3. If I plug a negative 3 in here, this is negative on top. And on the bottom, we're squaring it, but it's 9. 9 minus 4 is a positive number here, taking the cube root of a positive. So it's negative divided by a positive, which makes the first derivative a negative number. And that means that f of x must be decreasing on that interval. Okay, so far so good. Let's take in a negative 1. So negative on top, and on the bottom this is negative 1 squared is positive, but it's 1 minus 4 is a negative 3. We're taking the cube root of a negative, it stays negative. Negative divided by negative is going to make that positive. Which means f of x is increasing on that end. Oh, change colors, increasing. There we go. All right. I'm wondering if this is going to be completely symmetrical over this whole entire thing? Well, look at our intervals. They seem pretty symmetrical. All right, if I stick in 1, 1 here is going to be positive. 1 down here is going to make this 1 minus 4 is a negative number. Cube root of negative is negative. Positive divided by negative is negative. So f is decreasing. That's what that says. It says decreasing. Take my word for it. Okay, and then lastly, if I stick in a positive 3, 3 is positive up here. 3 is going to be 9. It's going to be a 5 there. Cube root of a positive is positive. Positive divided by positive is positive, meaning we're increasing on this interval. Okay, so just as a visual here, we switch from decreasing to increasing. We have ourselves a minimum here, relative minimum. Increasing to decreasing, we have ourselves a relative max. And then decreasing, did I say that right before? You'll have to rewind the video and see. Decreasing to increasing, we have another relative minimum at that particular point. Okay, so, and once again, if I were going to justify any particular one of these, let's say at 0, f prime, no, not f prime, f of x has a relative maximum at x is equal to, so this is getting really messy, x is equal to, what was it, 0, because f prime of x changes signs from, let's see, if I have a maximum, it goes from increasing to decreasing, the derivative goes from plus to minus for relative max. Changes from positive to negative at x is equal to 0. There we go. We just justified that we had ourselves a relative maximum. You can justify the other ones as well. All right. Now, let's go back to the fact that our function was defined for all real numbers, but the first derivative was undefined, was right here at positive or negative 2. Okay, and those were critical numbers. So what do you think the graph is going to look like at those particular numbers? We have ourselves relative minimums at each one. Oh man, did I just erase that? Yeah, we have relative minimums at each one of those points. It's continuous at those points, but the derivative does not exist at those points. What do you think the graph is going to look like? Let's take a look, shall we? All right, so here we go. Bloop. Ah, sharp turns. Does that make sense? It's continuous at those points, but the derivative did not exist, and we have relative minimums at those particular points. We had ourselves some sharp turns. So here's the graph of the derivative. You would have yourselves asymptotes at positive and negative 2 here, and you can see that we have ourselves another critical point there at 0. And speaking of that particular point, you can see that it is a smooth curve there instead of a sharp turn at each one of these, because the derivative and the original function existed at that particular point there. And if I take a look at the derivative in green, it changes from positive to negative at that particular point, indicating a relative maximum.